In this lesson, we'll be discussing the ideal gas model and how you can apply it to thermal fluids problems in this course. Now, the ideal gas model applies to only certain gases. They have to be a gas at a low density. They have to have a relatively low pressure, so by that we quantify that relatively low pressure to be a reduced pressure that is much greater than 1. Reduced pressure we define in the text as being its pressure of that gas divided by its critical pressure, where the critical pressure is the pressure at which it cannot go from gas to liquid. Knowing how the reduced pressure and how the critical pressure, what they are and how they work, is not necessarily that it's not that necessary for this course. However, it is necessary that you understand it should be a relatively low pressure for that gas, or the gas should be at a relatively high temperature. When it gets that high temperature, that reduced temperature greater than 2, it should also have a reduced pressure less than 8. So you can take some gases, some substances that might not normally in regular conditions and be treated as an ideal gas, but if you get the pressure low enough or you get the hot temperature high enough, you can then treat them as an ideal gas. So once you've established that something can be treated as an ideal gas, you can apply the ideal gas equation of state. Now in physics they use the equation of PV equals nRT. We use a modified version of this. So our equation for this course will be pressure times the volume is going to equal the mass times the universal gas constant divided by the molecular weight times the temperature. This is equation 1.41 in your text. Now this can be rewritten because, as we know, pressure is a intensive property, temperature is intensive, but volume is extensive, and we can actually turn that into an intensive property by dividing by mass. So if we want to make this whole equation just intensive properties, we can divide both sides by mass, and that gets rid of the mass on the right side, so we just have pressure times specific volume equals the universal gas constant over the molecular weight times the temperature. So this is equation 1.42, and this is the one we're going to use a lot more often in this course. Now when we say the R bar right there, that's the universal gas constant. There is actually a gas constant for each molecule that you could use, but it's easier for us just to use the universal gas constant and then divide it by the molecular weight for each of those molecular weights. The universal gas constant can be found on the back of your textbook. The molecular weight can be found in tables 1 and 1E. Now when you're using this equation, make sure you are using the correct universal gas constant and molecular weight based on what units you're using. If you're given information in SI units, then use the SI versions. If you're given it in English units, there is an English version for both the universal gas constant as well as the molecular weight. So make sure you're using the right constants based on the units you're in.